Okay, welcome back, my friends. I got my camera working on my computer at home, so I'm going to try this new method of taking notes. I think it'll be more efficient for us, and I can kind of do exactly what I want to do with showing you how to do things. So hopefully it'll help us a lot. Today we're going to talk about infinite geometric series. So what do these things mean? The last two sections we were doing things and labeling them as S sub n. That n meant we were doing it for a limited number of terms. So it was a partial sum. If we're doing an infinite series, this is for an infinite number of terms, a complete series. What did series mean? Series meant sum. Infinite means all the terms in a sequence. And geometric means we're only working things with a common ratio. So the topic today is pretty straightforward. I hope you feel like it will be simple, and once we get the idea of it, everything will be fine. Okay, sorry about that. I paused, so I've kind of lost my train of thought a little bit. But what we're doing is we're going to now find sums for sequences that have an infinite number of terms. And the way that that works is we can only find the sum for infinite series which are convergent, which are series which start with really big numbers, and as they go on further and further, so it may start with a term that's really big, and then as we come down towards 0, it's going to get smaller and smaller terms, and these terms are going to keep getting closer to 0. So we can find a sum for them because eventually those terms aren't going to add any value to our series. So what we're saying is, when we were doing questions last section, we were using that S sub n equals the first term minus the first term times the rate to an nth power over 1 minus the rate. So here, if we use that the rate absolute value, it could be positive or negative, if it is less than or equal to 1, what happens with this part, so when we use this specifically, as the rate gets increased, let's see, so if we have, maybe I can show it here, say we're using a fourth, which is a number less than 1. So as, well, let's do it this way even. Let's say 1/4 to the nth power, right? That's the rate to the nth power. So if I go into my table here and look at what happens, so our sequence would start at 1.25, and as we're going up through our sequence, these scientific notation numbers get increasingly bigger and bigger, so these are numbers that are closer and closer to 0. So this part here goes to 0 when we have a fractional number r, a ratio that is a fraction or less than 1. So what does that mean? What happens is we turn this into the first term essentially times 0, because eventually that's what it goes to, all over 1 minus r. So the sum that we're going to calculate, if we assume we have one of these things, our equation will become the first term over 1 minus the rate. That's going to be the sum for this section. That's what we get right here. When it's divergent, we start with small numbers and they grow infinitely. So we're going to continue as we go on through the sum, add numbers that are bigger and bigger. So this has no sum if the numbers keep getting bigger and bigger. So convergent series are decreasing because they have a fraction rate. Divergent series are increasing, and we cannot define a sum for a divergent series. So one of the things they might ask us to do, so just things to know. We're going to talk about the ratio, and we'll kind of come back to that here in a second. One of the things they may ask us to do is decide if something is convergent or divergent. How would we know? First of all, we'll know that the sequence is decreasing or increasing, and we will find the common ratios. Okay, so a convergent series is a ratio that's less than 1. A divergent series is something where the ratio is greater than or equal to 1. So if your ratio is in this group, you'll say convergent. If it's in this group, you'll say divergent. So let's, our step here will be always first determine your common ratio. Then if the absolute value of r is less than 1, then we're convergent. If the absolute value of r is greater than or equal to 1, it's divergent. Okay? So that's all we have to do when they're asking us, is it convergent or divergent? And something that I'm still noticing people are doing is choosing the wrong value to put on top. You always, always, always have to do the second term over the first. So for this one, we're checking for the common ratio. We'll take 360 over 480, and when we do that, okay, we do 360 divided by 480, and we get 0.75. So this is less than 1. So if we look over here, if the absolute value of r is less than 1, then this is convergent. And we check our series. What is happening here? These numbers in our sequence are decreasing. The sequence here. Okay, so the sequence is decreasing, it's convergent, we're going to be able to find a sum. What about this one? If we take 10/9 over 5/6, and if I'm doing that in my calculator, I'm going to make sure 10/9 divided by 5/6, that's 1.3 repeating, or I can hit math fraction, 4/3. This is greater than or equal to 1. That fits into the divergent. So if we were trying to find the sum, we would just say, this is a divergent series, we cannot find the sum. Okay, so that's the other thing, the main other part of the problems we're going to solve. You're still, in these problems, going to start by finding the common ratio. But we're going to try and find the sum, and if we can find the sum, we're going to use S equals A1 over 1 minus R, which was the equation that we discussed up here. This. Okay, we're going to try and use that. If that is the equation that we want to use to solve these problems, we need to identify A sub 1 and R for each problem. Okay, so find the sum of the infinite series. Identify A sub 1, identify R. So this one's nice and easy. They're giving us the sequence. So A sub 1 is going to be -3. We know that it is a sequence, and we can assume in this section that they're going to give us geometric sequences. So the rate here would be -4.2 over -3. Okay, so let's put that in our calculator. -4.2 over -3 is 1.4. So after you identify first step. Identify a initial, first term, identify R. Then 2, is it divergent or convergent? Well, here we got that R is 1.4. If R is greater than or equal to 1, it's divergent, and if it's divergent, there's no sum. So R is greater than or equal to 1, so divergent, no sum. That's what we come up with. Okay, and you're going to do that for each of these problems. So part B, a sub 1 equals 12 over 5. R equals 6/5 over 12/5. Okay, so 6/5 divided by 12/5 is going to be 1/2. So here, R is less than 1, it's convergent, so I do have to find my sum. So S will be, we said A sub 1, so that was 12/5 over 1 minus R. Okay, so I'm going to go ahead and just put all of that in my calculator at once. Where's my work here? Okay, so 12/5, actually, parentheses, I've got a fraction here. 12/5 divided by 1 minus 1/2. That's what they should all look like. Clearly, 1 minus 1/2 is 1/2, but just to practice knowing that they're going to be unusual fractions there, that's what we want. Okay, 4.8. You can find the fractional equivalent to that, or we can just use 4.8. Okay, so that is the sum, 4.8. All right, we are going to have some that come with this sigma notation. So we got to remember where to find a sub 1 and R. Okay, a sub 1 happens when we plug in the first value. It's not 1. We have to plug in that 1. So we will get 4/3 times 5/4. We plug in k is 1 here, 1 minus 1. Okay, so this is 5/4 to the 1 minus 1. Remember, something to the 0 power is just 1. So this is 4/3. The ratio, we can just pull from the problem. The ratio is always this number taken to the exponent. So that's 5/4. So we then have to decide, is this divergent or convergent? If the ratio is 5/4, that's bigger than 1. So you will say R here is greater than or equal to 1. It's divergent, so no sum. Okay, let's do the next one. D is also a sigma notation problem. So we'll start with a sub 1. A sub 1 is calculated when I plug in whatever k is down here. It won't always be 1. Could be any number. We're going to plug that in. So 5/3 times 3/7 to the 1 minus 1. So 3/7 to the 1 minus 1, or 3/7 to the 0 power, is just 1, so I can ignore that. A is going to be 5/3. R is going to be the rate that's taken to the exponent, or 3/7. 3/7 is less than 1, so I do have to find my sum. So my sum is going to be a sub 1, which was 5/3, over 1 minus my rate, 3/7. Okay, so let's put that in. We have 5/3 divided by 1 minus 3, whoops, not what I meant, 3/7. Okay, 1 minus 3/7 and 5/3. Alright, if it's not a nice number like the one we got before was 4.8, awesome. It's a terminating decimal, write it down. If it's not a terminating decimal, turn it into a fraction. So 35/12 will be my answer here. 35 over 12. That's my sum. All right, last one here. Identify a sub 1 and your rate. A sub 1's nice and easy because they're giving us the sequence. That's going to be 15/4. Your rate, always take the second over the first. So 5/2 over 15/4. Got to figure out what that is. All right, 5/2 divided by 15/4. Put your fractions in parentheses to keep everything nice and clean. And that, if you don't recognize it, is 2/3. 2/3 is less than 1. It's a convergent series, so we do need to find the sum. And we find the sum by taking a, which is 15/4, over 1 minus r. Okay, so we're going to plug that into our calculator. I'm going to get the light out of there. Okay, so 15/4 divided by 1 minus 2/3, or you can just write 1/3 in there, 11.25. Okay, that's my sum. That's the meat of the problems for this section, is deciding if something is convergent or divergent and finding the sum if it has one. Something that we will talk about really quickly that we've done this year already, actually, a little bit. Let's see if I can make that flat here. Okay, writing a repeating decimal as a fraction is actually an application of an infinite geometric series. So there's two ways to do this. We're going to do the infinite series method, and I will show you the old method that we do, which is a little more straightforward, but it's an application of that series. So you need to recognize that this is the same as 0.321212121, and so on. Okay, so what it's really doing, we could spread this out as a series. It's 0.3 plus 0.021 plus 0.00021, and so on. And then we can rewrite these as fractions. So this is 0.3 plus 21 over, how many zeros? 1, 2, 3. And then this is 21 over how many zeros? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So what is happening each time, we can find a common ratio between these things. Both of the examples on these notes are kind of a two-step problem. You may find one that doesn't have this additional piece up front. What happens is, this is unrelated to the sequence, so we're going to add that at the end. We're going to leave the 0.3 out, and we're just going to look at the matching, this piece where we see this pattern happening. So how do I get from this term to this term? This is a geometric series. The ratio would be 21 over 100,000 divided by 21 over 1,000, or okay, so 21 over 100,000 divided by 21 over 1,000, 0.01, or 1 over 100. That's my ratio. Okay, so we can turn this into a sum of this geometric series. So we're going to take the 0.3 because it's not related to my geometric series, plus the sum, which is the first term, the 21 over 1,000, over 1 minus my common ratio of 100. So this is 0.3. I can calculate the sum here, 21 over 1,000 divided by 1 minus 1 over 100. and I get that 0.21, okay, so that is correct. That part of it is 7 over 330. So we get 0.3 plus 7 over 330. Okay, so then we're going to do, I'm going to add 0.3 to my 7 over 330, and that gave me my original problem. So the fraction here is 53 over 165. That's our answer. Okay, flipping over to the second problem here, I can rewrite this as 2 plus 0.18 repeating. So I'm going to ignore the 2 for a minute, and I'll add that back in at the end. We just have to figure out what 0.18 repeating is. So the geometric series would be 18 over how many zeros? 100 plus 18 over, every time you shift over, you're going to add the number of zeros that are in your number. So if this were like 183, I would be adding 3 numbers. Okay, so it's going to be 2 more because I have a 2-digit number there. Okay, here it was a little different because we started a term over, but then we were adding 2 zeros. So we had 1, 2, 3, and we made it 5. The next one would have 7, and the next one would have 9. Okay, and so on. So you might notice we're adding 2's. Your ratio is going to be the same, and you can check that by taking 18 over 10,000 over 18 over 100. Your ratio is still going to be 1 over 100 when you divide that out. So our sum will be, for the geometric series, and then remember we have to go back and add the 2, it's going to be 18 over 100, my first term, over 1 minus 1 over 100. Okay, trying not to get my kitchen light in there. Alright, so 18 over 100 divided by 1 minus 1 over 100 is, good, we have to turn that into our fraction. This is 2 over 11. So adding the 2 back in gives us 2 and 2 11ths as our final answer. Now you may remember the other method that we used to do, which just assumes the entirety of this process. That was the algebraic method, which we've done before. You will put it over so you place the numerator over 9's. Let's just say that. Because what are we doing? What is 1 minus 1 over 100? 99 over 100. Okay, so all you're doing is you're taking this first piece. This is over 100. This is 99 over 100. So we're going to put 18 over 99. Alright? So if this was a 1-digit number, you'd put it over 19. If this is a 3-digit number, you would put it over 3 9s. So however many 9s are in your number, you put it over that. So we end up getting 18 over 99, which needs to be reduced to, these both have 9's in common, so 18 divided by 9 is 2, 99 divided by 9 is 11. That's where this 2 11ths has come from, and when we add the 2 back in, we also get 2 over 2 11ths. But the key here is all of this process, this algebraic process, comes from geometric series and the calculation of those. Alright, so for today, I just want you to work on the homework problems. I'll also put up the link for the worksheet if you want to work on that. And next week we start classes where we only have 3 days a week. So on Tuesday, I will have the quiz posted for sections 3 and 4. So you really have a long time to work on these problems. I'm just putting the due dates up there so that the system tells me that you've turned something in if it's beyond the time when I start grading them. If you have any questions, please feel free to email me, make a Google Classroom comment. If there's anything we're really struggling with, I will try and put another work video up where we work some problems. All right, good luck, guys. Enjoy.